All right, so thank you for being here on Monday morning. So now, okay, I realize that it's just in the shade, the title, but the idea is that it will be upstairs for the rest of the talk, so I hope that's okay. This is an update on something that I've talked about here, I guess last February or so. So it's the q-deformed Haldane-Shastry model. The Haldane-Shastry model started in the late 80s. This is a long-range spin chain. And the q-deformed, so it's like the XXZ-like version of this spin chain. That so somehow this work was actually started not so long after Haldane-Shastry spin chain became fashionable by work of Vincent and others here. And a few years later, Dennis Uglov actually managed to find this q-deformed version. And he wrote a paper about this, but somehow this paper was never published, and it was a bit, so it kind of, people forgot about it or never really noticed. And so I was interested in this for some reasons a few years ago, and I happened to find this paper, and it did exactly what I wanted, and I started looking more and more into it, and I managed to reformulate this model in a different way. And since then, I've been working on this with Vincent and Didina, who will be here from tomorrow onwards. So I'd like to tell you a bit about what we're trying to do this week. So it's also about work in progress. Of course, ask any questions that you have. So it's a spin chain, but actually more generally, rather than just taking SU2 with spin a half, you could look at an SUN chain, and then you have sort of not just spin up and down, but you have sort of n colors if you wish. And I take L sides. So the Hilbert space is just L sides with n-dimensional local space. And for example, which is sort of the main example, if n is 2, then we just have these spin up and down at each side, of course. So let me first write down the Hamiltonian, and then I will discuss some properties, and towards the end, get to our conjecture about the exact finite size eigenvectors that we have. So the Hamiltonian on this Hilbert space looks as follows. Where do I want to write it? I guess I can do it here. So it has a long-range pairwise form. So it's a sum over pairs of sides from 1 up to L. Then there's some potential for I and j, and then there's some long-range spin operator that I will get to in a minute. And I denote it by S with an interval I, j. So these are the spin interactions. So first, the potential. This is quite simple. So one way to write it is as follows. It's, I will write a fraction. So it's the denominator is q zi minus q inverse zj times q inverse zi minus q zj. And in the numerator, there's zi zj, where I write throughout this talk, I'll write zk for the kth root of unity. So 2 pi ik over L. So I think of this spin chain as sitting in the unit circle in the complex plane, and then the sides, the positions of the sides are labeled by these zk's in the complex plane. And the pair potential has this form. So let me actually give you some sort of geometric picture of what this looks like. So first, the case Q is 1, which is just the ordinary Haldane-Shastry model. I will try to do this in orange throughout. So for Haldane-Shastry, this potential is just of the form 1 over r squared, where if I draw a part of the circle, so here we have all these sides. Of course, it's a whole circle, but I don't need all of it. So if here there's some side I less than j, then r is just the chord distance between these two sides for q is 1. So it has a nice an inverse square of the chord distance between the sides in this case. Next, let's consider the case when q is purely imaginary, let's say with positive imaginary part. Then V now has a 1 over r plus r minus, so sort of a point split form, where if I draw the same segment of the circle, so this is where I was, and this is where j is. And now we think of this I and j, and there's a little sort of dipole. So we sort of, this becomes a little rod, like that, and like this, where this is q inverse zi, this was just zi, and here we have q zi, and likewise here we have q inverse zj, here we have zj, and then here's q zj. Then you see that from sort of there are two distances, sort of a closer distance, a shorter distance and a longer distance. And the shorter distance here is exactly, has length r minus, and the longer segment here has distance r plus. So it's sort of also, it's like a, somehow it's like a, I don't know, an geometric average of these two distances between the sides, if q were purely imaginary. And of course, in general, these rods will turn around. So in particular, in case q is real, let's again say positive, actually let's say larger than 1, then it's still of this form, where now the picture becomes, so we have this side zi and zj, let me not draw all the others, and now we have to draw q zi will be here, q inverse zi will be there, here we have q inverse zj and q zj, and now there will be a distance from q zi again to q inverse zj, and one like this. And in this case, actually, these two distances are equal, so there's also, they're of length r plus minus absolute. Yeah?
There are two dipoles.
Yes?
And the charges of the equal charges they are repulsive. No?
Well, right, so I'm making this, so I just want to give sort of this geometric interpretation here, where you have, so this is just how these distances are sitting there. So I'm not really thinking of them as really as dipoles, but just like little rods, and the interaction happens to be like this. I don't know if it should be, if it would really be possible to make it even more precise like this. But here at least you see that this q, when it's not equal to 1, it's a little bit like you sort of really split this point into a little rod, and somehow these are the distances that it talks with. All right. So this is the model with the potential, and now we get to these Sij's, and I'll do this on the other board. And they're a little bit more complicated. So first of all, let me actually draw it here. I have a sort of a pictorial way in which I'd like to remember what their structure is. So let me first draw this pictorial way, and then I'll tell you how this actually, what this actually really means. But then it's good, we already have it on the blackboard for a start. So now I will draw, this was the chain seen from the top, let's say, and now I will draw it from the side with sort of time going up. So these are the world lines, if you wish, of the sides. So here, there's a world line, which I will label by zi again, the position of the ith side. Then there will be, well, a bunch of other sides. Here will be zj. So beyond I and j, nothing happens. So what now happens is that zj is moved over here, exchanged with these other guys, pictorially like this. Then it interacts with some wiggly line like this, with zi, and then it's moved back. And these little arrows, they're just to show you what the direction of time is. Up. So the picture is like this, and here's zi plus 1, and so on, and the parameters end up at the same position at the top. Right, so what does this picture really mean? Well, the idea is that this deforms, so I had my orange color somewhere from this. This will be a deformation. Let's see if this is also possible. Well, okay, it's slightly tight, but let's do it. So if q goes to 1, then this just will become a long-range permutation of ij minus the identity. So it's an exchange interaction where the sides, the spins at side I and j, they will be exchanged minus the identity. So it's sort of like anti-symmetrization. And this will actually be a q-deformation of the decomposition of this thing as, well, let's start here. First, you move the side, the spin at side j to j minus 1. Then, well, and so on until you move it to side I plus 1. Then your nearest neighbor interact with I minus the identity. So that's what this wiggly line will mean. And then you transport it back 2-side J. Okay, so that's what this picture will mean, but somehow we're deforming this. So in general Q, what we use for this is we use the R matrix. Actually, technically, it's the SLN-affine. So the quantum-affine version of SLN R matrix. And rather than doing this in general, let me just write it down explicitly what it is in case you just have SL2, so with the normal spins. So then this R matrix acts on C2 tensor C2. So it's a 2-side operator, like the permutation here. And R check, this is the one that I will work with. So it's the braid-like version. Depends on the spectral parameter U. And it's a 4x4 matrix with non-zero entries that I denote by 1. U times G of U, F of U, F of U, G of U, and 1. Where F of U is the function U minus 1 over QU minus Q inverse, and G of U is Q minus Q inverse over QU minus Q inverse. Right, so if Q goes to 1, then this function, this just becomes 1, and this becomes 0. So this just becomes the 2x2 permutation. So that will be the generalization that we have here, which is here in the picture. And this wiggly line, the generalization there, actually turns out to be Q minus Q inverse times the derivative of this R check at U equals 1. So you can also compute this. It's even simpler. It's 0 minus Q inverse 1, 1 minus Q 0. So you can check that this, when Q goes to 1, goes to permutation minus the identity, which is the isotropic, just to connect it to usual spin chains. It's 1/2 times the sum over spin x, y, spin in the x, y, and z direction of sigma alpha tensor sigma alpha minus the identity. Right? So this thing Q deforms this normal exchange interaction for nearest neighboring sites. And the R matrix itself does the transport between nearest neighbors. And so if you really know just about the normal Heisenberg XXZ model, let's make that even more explicit. So the usual XXZ doesn't quite look like this. So XXZ usually has this parameter big delta, which is in this notation Q plus Q inverse over 2. And then the connection between this R check matrix and the usual one is that the permutation times this R check of U is conjugate. So sometimes people say gauge transform by some exponential with Pauli Z over 2 in the first leg. Then here, okay, it depends a bit on the normalization, but let's say you take the 6 vertex or XXZ R matrix at lambda. So here U, I'm taking U equal to e to the 2 lambda. And then this R matrix, so usually I put ABC vertex weights in here, so I have to normalize so that the vertex weight for A becomes 1. So maybe it's like this, and then we have the inverse of this factor there. Oop. Tensor 1. And as a consequence, R check prime at 1 is the usual XXZ Hamiltonian minus Q inverse over 2 times Pauli Z in the first factor minus 1 times Pauli Z in the second factor over 2. Okay, so what I really mean is that usually if you've worked with the Heisenberg spin chain, then the normal XXZ spin chain doesn't have this asymmetry with just a Q inverse here and a Q here, but it has actually just a minus delta here and a minus delta there, so, right? So you have to sort of compensate a little bit, and that's precisely what this extra factor here does. Now, normally for the Heisenberg spin chain, this is this story by Vincent and Saleur, that you can compensate the normal XXZ interaction with the delta here and here by this poly z in the first or in the second factor, and if you only have nearest neighboring terms, then you have these telescoping sums. So these terms cancel pairwise between neighboring summands here, and you just get some boundary terms. And this is known as the temporally leap spin chain or a quantum SL2 invariant spin chain. So that's the one that you get from this R matrix. This is maybe the better algebraic point of view for it. But if you go to higher rank, then you still have the solution of the Young-Baxter equation, or the quantum Young-Baxter equation, still has this form with this asymmetry, this imbalance between the U, G versus just G here, which is what causes the Q inverse versus Q here. But in general, you won't be able to do such a simple gauge transformation to just get rid of this single exponential there. And so actually, this is the better version for higher rank as well. Well, sort of suitably upgraded to higher rank. But I think you either know this or it's not really worth it just to explain it now. So then we can just stick with the n equals to 2 case. Right, so this is the R matrix. And what do we need this for? Well, okay, so this obeys the Young-Baxter equation and the braiding unitarity and some initial condition. So now we can interpret this picture using this R matrix if we have the rule that such a crossing where the spectral parameter U and V switches places, if this would be R check of U over V, and we also need this Q minus Q inverse R check prime of 1. So this is this with the wiggly line, and now the parameters stay in place. So interpreted like this picture tells us exactly how the long-range interactions are. Now let me actually make this more clear with an example. So if we have a long-range interaction from site 1 to 4, so let me redraw the same picture. So here we have this with an R matrix, with an R matrix. We have 4 sites like this. All right, so this is just the same picture. We have parameters Z1, Z2, Z3, Z4. Okay, so we start at the bottom because time goes up. So here we have an R check prime, just an R check in spaces 3 and 4. They stay in place, by the way, of the left parameter over the right parameter. So it's Z3 over Z4. Then this Z4 is now here, and the Z3 is sitting here. Next, we have an R check matrix at sites 2 and 3 with parameters Z2 over Z4. Then Z4 moves over here now. We have this interaction term. So this is this Q minus Q inverse R check at 1, 2 prime of 1. Then here we have another R matrix. Z4 now comes from the right, and Z2 comes from the left. So this is an R check at sites 2 and 3 of Z4 over Z2. And finally, we have an R check 3, 4, Z4 over Z3. So this composition, where this is really at the end and this is at the beginning of the line, this is precisely how these long-range q-deformed spin chains, sort of the q-deformation of this exchange interaction.
So is H going to convert to QQSN?
Het even, yes. Yeah, exactly. So your question, well, so you know that this R matrix can be written in terms of, for instance, in terms of the Hecke generators. So you immediately see that this entire expression is actually an element of this. You can write it lives in a representation of the Hecke algebra. Actually, you can even write it via temporally leap if you like. This is immediately temporally leap, and this is also some linear combination of temporally leap and identity. So this Hamiltonian is actually, it's basically already written as an element of a temporally leap representation of the temporally leap algebra. So you see that it has to commute immediately with UQSLN. And then the het, this is more complicated, but it will even have quantum-aaffine symmetries. Yeah. Okay. So this is these long-range exchange interactions. So the physical picture is basically, well, this picture. So the idea is that really rather than just long-range exchanging, which is what you did for Haldane-Shastry, what you have to do is you have to go along the boundary. So you really go like, or actually the other way around. You go like this, then you exchange, and then you go back. So this R check it arranges some sort of transport, and R check prime is the nearest neighbor normal q-deformed exchange interaction, and then you transport back. And this R matrix with inverted arguments is actually the inverse of the R matrix, as you can check.
And the chain is periodic?
Right, so the boundary conditions, let me get back to this in a few minutes, yes, because this is not so completely clear what happens with those. So let me actually try to make a list with properties, two of which have already been commented on. Okay, so first of all, even before we go there, this transport by the R check matrix, so here you see that this, for instance, the spin at site 3, it's moved to the right and then moved to the left. If this were just normal permutation operators, it wouldn't have actually noticed this at the end of the day that it did anything. But the R check matrix is more complicated, as you can see. So actually, these intermediate spins, they do feel that something has happened. Another way of saying this is that these are actually multi-spin interactions. So it's not just pairwise interactions, but now we have for general n, spin with quotes, interactions for q not equal to plus minus 1, which is due to the transport by R check. Well, all right, next. You can check that this Hamiltonian is actually Hermitian for q real, which is quite clear from this formula. It happens to be anti-Hermitian when q is purely imaginary, so this covers these two cases, at least for q is I. Other roots of unity is actually not Hermitian or anti-Hermitian, but the spectrum does seem sort of nice, so I think it should be possible to do something with it, but I haven't really figured out how to really. So for q real, it's Hermitian, and then it's actually anti-Hermitian when q is equal to I. So at least, and this is sort of quite interesting. So running ahead a little bit, the Haldane-Shastry model is known to have very, very highly degenerate eigenspaces. This one, the q case is quite highly degenerate, but Haldane-Shastry is even more. These roots of unities, they're even more highly degenerate, have even more highly degenerate eigenspaces than Haldane-Shastry. So it's really, quite spectacular. Right, so it's actually, I'll get to that as well. It's sort of like a free anionic model, if you wish. Yes. Good. So regarding the boundary conditions, so the best that I can say about it at the moment is that it's actually some sort of twisted or quasi-periodic boundary conditions, which can be, the way that I have to see it at the moment is as follows. So let's write these zi's that I had, or zk, as omega to the k. So really, for us, omega is just this primitive root of unity. But I want to go away from this and formally take some limit. So let's formally send this omega to infinity. This will immediately destroy a lot of the symmetries of the model, but at least you can do this. It makes sense from the point of view of the Inno-Zemtsev. There should be a q-deformed Inno-Zemtsev spin chain, which I'm also interested in. And this makes more sense from that point of view. But what is nice about this limit is that you can check that omega times this potential that we had actually becomes a Kronecker delta, forcing basically interactions to disappear unless you're nearest neighbors. Which means that out of all these interactions, these Sij's, I has to be next to J. So in almost all cases, we're just left with this zigzag thing here, which is just this interaction, which is the usual Templey leap interaction. Okay? So what this means is that here you get the usual, this Templey leap XXZ chain, except that there's also this term where you have S1, L. Because on the chain, really, these are also nearest neighbors, and this is this also survives in terms of this limit. And what happens there then is that, so these are the boundary conditions. These tend to, in your papers, for instance, what you call this braid translation. So you formally add one, or you add one element, you enlarge in the temporally Lie algebra. So these are braid translations. With the no blob operator, if you wish. And so these are twisted periodic boundary conditions from the normal Heisenberg point of view, special twisted boundary conditions which preserve this quantum SLN symmetry. So this is a very sort of a formal limiting case of the chain that I have here. So I think so now, of course, I got rid of this. I took the braid limit, really, of the spin chain that I have here. So more generally, we can actually do something else. Because there is a version of, well, you can sort of simulate translational invariance, like with the inhomogeneous spin chains. There is a sort of something that takes the role of a shift operator. But let's see, what do I want to keep? Ideally everything, but that's kind of impossible, so let's keep this for now. All right. Oh, well, I hope that you remember this part. Right, so we had Q minus Q inverse R check of 1 was this zigzag, and the parameter stayed in place. Okay, V. All right, so the next point is that when Q is not equal to plus or minus 1, we deform translational invariance. So there's a left Q, what I call the Q shift operator. And it's defined, again, in terms of these pictures, as the usual left shift operator. Except that we have to put these parameters, Z1, Z2, and so on here. In this case, they're actually shifted a little bit. So now Z2 ends up there. Then we get ZL, and then Z1, finally. So this is R check L minus 1, L Z1 over ZL, all the way down to R check 1, 2 of Z1 over Z2. So this is an operator acting on the Hilbert space. And this is, at least when Q is real, this operator is unitary, meaning that its eigenvalues are of the form e to the IP, with P a version of momentum that let me call it Q momentum. Moreover, by the Young-Buxton equation for the R matrix, if you put U on top of each other of itself L times, you just get the identity operator. You can pull straight all these lines, which means that you use this Q momentum is quantized as usual for particles on the circle. So there's sort of the notion of momentum gets deformed a little bit, but there's an operator which formally takes the role of everything that you need to have this translational invariant setting. And this has a nice consequence that actually, now I just go to n equals to 2 for definiteness, but that should be easy to generalize. In the one particle sector, so if the total spin is 1 lower than maximal, or capital M is equal to 1, it's easy to write down the eigenvectors explicitly. So for normal spin chains, the Heisenberg model, you know that by translational invariance you have Macdonald as a solution. Now you can just do the same, and you can use this shift operator as the right shift operator to create these Macdonalds. Well, I hope that you sort of trust what this U was. So we get a notion of what I call Q Macdonalds. Actually, I guess I should call them quantum-aþine Macdonalds, maybe. So, and they will have momentum 2 pi over L times M, with M some integer, this integer here. And they're just a sum from I to is 1 to L, Zi to the power M, U to the 1 minus I, acting on the vector where the excited spin is all the way on the left, and then everything is up. So to understand this, let's first take this Q goes to 1 limit. So then this becomes the same sum 1 to L zi to the m, and now we just have spin up everywhere except at side I. Right? U was a left shift operator, so this is basically U inverses, so this will be a right shift operator there. So you see that in that case, the excited spin is just transported to side I. In general, for general Q, this is not quite the case. This spin is actually transported, but by this R-check matrix. So it's sort of, it's like with these multi-spin interactions. It can sort of fall off along the way already. So it can actually end up anywhere from side 1 to side I here. So actually, if you really write this in terms of really just in the usual coordinate basis, then this actually, well, it would look a little bit different. You would have to resum, but then the wave functions are not nice. Whereas here, so what I want to do is I want to call this, well, this is sort of the better version maybe of the coordinate basis, and then here you just have plane waves. Recall that the zi, it was just, the zk were just the kth roots of unity. So here you have zi to the m, so these are just plane waves with momentum 2 pi over L times m. And it's very easy to see. If you just act on this with u, you raise this power, you rewrite the sum, you take out 1 power of z, so this omega, or sorry, z to the, well, omega to the m. So you see that you precisely get this, you have this momentum. So this is a simple computation that you can do in 2 minutes on paper. So this is kind of cool. And moreover, since at least for Q real, this operator was unitary, it follows that for Q real, these are orthogonal, and therefore they actually are eigenvectors of the Hamiltonian already. So you can compute, well, actually I cannot compute by hand yet. It's kind of complicated, but I can check, and from a different way, we know that they reproduce this dispersion relation that Uglov found already in '95 for the chain. So the energy with corresponding to this momentum is 1 over q minus q inverse times L times 1 to the q, 1 minus q to the minus 2m over 1 minus q to the minus 2l minus m. So if q goes to 1, then this denominator goes to 0, but this also goes to 0, so you have to do some computations. And you can check that when q goes to 1, this has the limit a half m L minus m. So essentially it's quadratic in the momentum for Haldane-Shastry. And you see that Q deforms this a little bit. So basically for Haldane-Shastry, this looks like a parabola like this, if this is the momentum, or the Q momentum from 0 to 2 pi, and this is the energy. And for general Q, it gets shifted a little bit like this, or like this, depending on whether Q is larger or smaller than 1, for real Q. Right, so this is kind of nice. So by this version of translational invariance, and in a way you could say that this is a version of periodic boundary conditions accordingly, we get these one particle exact eigenvectors. Right, so before I go to write down our, well, conjecture, I think we should say at the moment, for the exact general eigenvectors, the highest weight eigenvectors, let me quickly review the last few properties. So one thing that I mentioned, and I don't want to comment on more now, is that at finite length, there are a lot of symmetries. So this chain actually has quantum-affine SLN symmetries. Technically, I think I should put a little prime here, which means that I don't have this this central charge acting. It's just the representation that you get from some R matrices. So this is the usual sort of, that comes from a monodromy matrix. So, but this commutes with this Hamiltonian for any length, finite length already. So it has many, many more symmetries than the Heisenberg model, and accordingly the spectrum will be highly more degenerate. So actually this spectrum is more degenerate than the Heisenberg XXX spin chain, because it has these affine symmetries in addition to just UQ SLN, for real Q at least, or generic Q.
It's the same as for Q equal 1, the same
well, almost, except that for Q equals to 1, you have this very simple quadratic dispersion, so you can accidentally reproduce the same eigenvalue in different ways. So there are actually additional accidental degeneracies for q equals 1. But it's sort of, well, yeah, but it's quite highly degenerate. So let's say a little bit about this spectrum. So that's another property that I think I can.
I had a question on the shift operator. When
Sure.
Q is purely imaginary,
Mm-hmm.
don't you still have U to the L equals 1?
So u to the L equals to 1, this just depends on the Young-Baxter equation. So this is true for any value of q.
So it's just that U becomes not unitary.
That is true, yes. Yes, that's actually true.
But that has the momenta still.
Right, so you could still formally, you can still define the momentum to be this eigenvalue and it will be complex, and yeah, and the rest of the story actually pulls through. Except that I think they don't become, so they're no longer orthogonal for general values of q, these eigenvectors.
Energies are still real?
No, no, they will become complex. It's kind of cool, so if you, so I didn't really, well, this is something that is on my to-do list, but I haven't got around to doing this. But if you actually just numerically say, look at the spectrum, so the energies will be complex, but, so now I forgot. So there is a case, maybe q equals, so this is the complex plane for the energies, the energy eigenvalues. Then for some values of q, for some nice root of unities, they will look, for instance, there's one case in which you get sort of, well, usually they're made up of these kind of strings, and these strings even form, in one case, they form a sort of triangle. And in another case, they form a sort of diamond like this. And then for kind of higher roots, more complicated roots of unity, so this was maybe for the, well, maybe for I, that was very simple, and for the third root of unity is very simple. If you go to more complicated roots of unity, then these pictures, they're a little bit, they become kind of cool. So they become, well, I can't really draw it, but for instance, you get these sort of patterns where there are lots of eigenvalues sitting on these kind of little, I don't know, they're little, not quite fractal, but kind of very cute little pictures. So they still seem to have a lot of structure, but I don't really know how it is. So I don't know if I can do something with it. I think so, but I don't know yet how to do this.
Thinking of your dispersion relation there, Haldane.
Yeah.
Well, if Q is complex, what does it mean you have a complex dispersion relation?
What this physically means, I don't really. You mean physically, or?
Yeah, what does it mean?
I don't know. So I think at the moment, the best physically, you should only ask me about real Q or maybe Q equal to I. That's things that I can really answer, because then the Hamiltonian is Hermitian or anti-Hermitian, so I can make sense of the spectrum and everything else. For general or generic Q, mathematically everything pulls through very nicely, but I don't really have too much to say about this now. Okay, so let's actually say something more about the spectrum, and this is true for general Q as well, actually. So for finite length, the spectrum is very simple to describe, so the eigenvalues. So firstly, it is strictly additive. Let me comment on the word strictly in a moment. So the energy, when you go to higher magnetization, is just the sum of these single particle excitations, energies, and the momentum likewise is the sum of the single particle momenta, modulo 2 pi. So, but the interesting thing is that the rule, so this is this is something like you have for the Heisenberg model. If you do the beta ansatz, you also have this additivity. But there you have to solve these sort of parameters. They satisfy some constraints. They do so too in this case, but they're very, very simple constraints. So the analog of the beta equations has the following solution. The only thing, so these MR, so we just choose some integers up to MM from 1 to L minus 1. And the only constraint that they have is that for rank n, they have to be sort of far enough apart. So MR plus n minus 1. So what this means is that if we just draw L minus 1 circles, I can have, so this is maybe M1, I choose this circle. Then if I have rank, so n, if I have n equals to 2, this constraint says that I cannot not have two circles. I cannot choose two circles next to each other. But I could choose, for instance, this guy, and I could choose this. So this would be allowed for any rank. If I have an SL3 chain, then this condition says that I can have at most two next to each other. So this is okay for SL3, but not for SL2. But it's okay for any SLn higher than 3, and so on. So in general, this condition just says that for SLn, you can have at most n minus 1 of these circles next to each other. The physical picture here is that it's a little bit, you actually have anyons. So if you would have bosons, you could choose the same quantum number here many, many times over and over again. If you would have fermions, then once you choose one, you cannot choose it again, but you can choose the next circle or whatever. Now you see that these circles, they have a sort of a little bit bigger, they take up a little bit more space in phase space, if you wish. So the physical interpretation is that these are anyons, that you have some fractional statistics. So for SL2, Haldane showed for the Haldane-Shastry model that these are semyons, so they're halfway between bosons and fermions. And these rules, they say the same for any value of Q. So this is very simple. So this is, if you wish, the solution to the Betti equations. And the physical significance of this is that these energies and these momenta, they're really, really additive. If you combine two particles, their energy and their momentum is just the sum of the independent energies and momenta. So the physical picture here is that you have an ideal gas of anyons, if you wish, of particles with some statistics, some generalized Pauli principles that says that this is the only constraint that you have for choosing the quantum numbers, and that's it. So there are no bound states and so on. So it's very simple from that point of view. Good. So this was found by Haldane in '92, and it holds actually for any value of Q. So this is very simple. And so these are the energies, and this was also found by Uglov in '95. So what we are doing now is that we also have, we have a conjecture for the corresponding highest weight. So we have this quantum-aþine symmetries. So you have to find the highest weight vectors for these symmetries, and we have a conjecture for those as well. So I wanted to finish by writing them down. This is a little bit more technical, but I think it's kind of very cool because this chain is quite complicated with these multi-spin interactions. The spectrum is simple, and we can actually write down the corresponding eigenvectors. But maybe before I do so, are there any more questions? Okay. So then, I think I'm going to erase this for sure. I will need some more space, but I'll do that later then. All right. So the conjecture that maybe at the end of this week we'll be closer to having a proof is that for SL2, the exact, really UQ SLN SL2 at highest weight eigenvectors are as follows. So if we start with one of these motifs, by the way, the degeneracy was known, so you know exactly, there's a simple way of computing how many descendants there are. So really, once we know this, we know everything at finite length. Well, in terms of the spectrum, we know everything about the spectrum. All right, so this looks as follows. It's a sum. So I'm going to write down something that looks a little bit like I'm writing down a vector with respect to the coordinate basis, but it will be q-deformed coordinate basis. And then the wave function, there will be some Hecke things everywhere. Notice that this condition of having I1 less than I2 and so on means that IM is at least M. Good. So now I'll explain what this is in a second, but it's a Hecke generator acting on polynomials, going from I2 down to 2, 1, and so on. Hecke acting on polynomials from IM, M plus 1, M. So these are Hecke generators acting on a wave function labeled by a partition lambda, which will be related to this motif. Whose arguments are the positions of side 1 to m only. So it's like everything is sitting on the left in the spin chain. We had L sides, but somehow we put all the excitations only at side 1 up to m. And then here we transport these excitations higher up. It's a little bit like what happened with these Macdonalds, where I put the excitation on the left and then I transport it. But here I transport it with the shift operator. And here, so I hope that we will be able to write it in terms of the shift operator, but at the moment we have transport by the Hecke operator. And then this is just sort of the wave function. And then we get this q coordinate basis, which is Hecke acting on spins with the same structure otherwise. And then I do exactly what I just said. I put all the excitations on the left, m of them, and then the remaining L minus m on the right. And I act with these Hecke generators to move them to where I think of having the excited spins. So this here, I want to think of this as sort of a q version of the coordinate basis. Because, well, let me write this down. So basically, these will just become normal permutation operators or shift operators. So this will become exactly the normal for q is equals to 1. This will just be excited spins at site im down to I1. But in general, now rather than by a q shift operator, the one built from the R matrix, we have something built from these Hecke generators. All right. So I've been talking about Hecke a lot. So let me write this down. So we have a Hecke algebra acting in two ways. So first of all, I use this notation where t, either for polynomials or spin, for some j down to I. And this just means j like this down to I like this. And before I explain what they are, just to make more clear this structure, if you take q equals to 1, this just becomes a permutation, a cycle, like this. And this decomposition just is the usual decomposition for cycles into nearest neighboring transpositions. So here I choose for instance, and it doesn't matter which one I choose, but I choose for instance this decomposition. So this is in the symmetric group. Now this Hecke stuff is a q deformation of these permutations. And it acts in two ways. So I have it acting on spins. So then this ti on the right, with just one subscript for spin, it acts on, well, this Hilbert space with L sides of spin 1/2 in this case, because we're at rank 1. And then it's a matrix that looks like this. Acting at neighboring I plus 1. So this is what you get from this R check matrix that I had before in the braid limit, where you send u to infinity up to a factor q. And when q goes to 1, this also, just like the R matrix, becomes a permutation operator. So now you do see that this second line here, when q goes to 1, this thing here just goes to excited spins at site I1 and so on up to IM. But in general, it's sort of this funny transport. And then we have Hecke algebra acting on polynomials. Okay, so this is minus q zi minus q inverse zi plus 1, partial I, which I will write down in a second, plus q. And when q goes to 1, this is deformation of acting on polynomials. So it will deform something that I denote by sigma I, which just swaps zi and zi plus 1, right? So this is the natural action on spins, exchanging spins at two sides. This is the natural action on polynomials. You just switch two variables. And then in terms of this sigma notation, this partial I is the divided difference. So it's anti-symmetrization like this. And if I'm an anti-symmetric polynomial, I know I can divide it like that. So this still gives a polynomial when acting on polynomials. And this is called the divided difference. OK, so this is just, you can check that this actually, both of them, they obey the relations of this Hecke algebra, which is this q-deformation of the symmetric group, with, in particular, next to the braid relations, the condition that t I q minus q t I plus q inverse is 0. This is the Hecke condition. So you can check that both of these obey this. So we have two different representations of the Hecke algebra. And one of them here acts on these spins to transport sort of the excited spins to the right in this q fashion. And likewise, here you have these Hecke algebra acting on polynomials, basically transporting or exchanging, well, q exchanging these z1 up to zm for zi up to zi I1 up to im. Except that just like with the spins, you can actually end up with sort of lower zi's as well, because you have this q deformation, which is, yeah, it's not just a permutation. It's not just swapping coordinates, but it's sort of, it's a linear combination of swapping and not swapping with some coefficients involving q. OK, so it's not super simple, but on the other hand, OK, so you have to dress these spins with this Hecke stuff, and you have to dress this polynomial that I'll give in by this Hecke stuff here, but it's not terribly complicated. Now, finally, let me write down this polynomial. Blip, blip, blip. What do we keep? I guess we should keep the Hamiltonian, but this is clear. OK, and the potential also goes. All right, so just finally, to make this complete, psi lambda of z1 up to zm. This is, first of all, not so important product of these zi. So this is like a center of mass motion part, free motion. Then there's a product over I less than j up to m. And then there are two q-Vandermondes, basically. So this is a q deformation of the Vandermonde. One with parameter q and one with q inverse, so that the entire thing is invariant under inverting q. And then finally, we get a Macdonald polynomial of lambda with variables z1 up to zm and parameters q and what is usually called as t equal to q squared. So I'm not really going to explain what Macdonald polynomials are, except that they are some orthogonal polynomials, symmetric polynomials. So they're very nice functions, and lots is known about them. And so this is something that is very explicit, actually. So it's not, if you go to a high number of sites and excitations, it's not very simple to compute this in practice, but it's very explicit. The computer can actually do this. So it's just a recipe for the solution. And there are no Bethe equations that you have to solve. There's just this very simple pattern of m's that you have to put in. So the final thing that I have to say is, what is this lambda? So lambda here is m member weak partition. So I'm allowing the value 0 here. And for instance, if my motif is, I chose this one, so this is m1. Then I choose this one, so that's m2. Then I choose a bunch of others. And finally, I have my last bullet that I chose, and some more things here. Now let's compare this to the left. So here, these spins were sitting leftmost, the variables were leftmost, and we're also comparing this to the leftmost motif. So the leftmost motif for SL, remember, we're SL2, so I can fill the first side. Then I have to keep this empty, but I can fill this guy. I have to keep this empty. I can fill this, and so on, until I have the same number of bullets here. So this is 1, 3, 2m minus 1. And then everything else is empty, so I have the same number of bullets. Now, if we compare these distances from the leftmost filled thing to the actual motif that I have, then if I go the other way, because these are decreasing, whereas the m's, they are increasing. So if this is, now this is lambda 1, lambda 2, and so on up to lambda m. So you see that lambda could be 0 in case you're sort of leftmost. You also see that if you move, if you want to move this bullet, you might have to move this bullet here, right? Because of this sort of exclusion rule. You can't have too many things next to each other. So this precisely ensures that these lambdas will have this rule here. We're just for SL2. So this is the rule. So here I have a weak partition. I know what the symmetric Macdonald polynomial according to this is. The Macdonald polynomials have two parameters, q and t. So q is t squared, t is q squared. If q goes to 1, then this becomes a Jack polynomial with this parameter. So this thing here goes to Jack of the same partition with this parameter alpha equal to 2 of these variables. All right, so it's a little bit of a beast, this explicit highest weight vectors. But on the other hand, this is a rather complicated, long-range spin chain. And so for now, I've numerically checked this up to 7 sites. I've checked this completely, that this reproduces the full spectrum, so all the possible eigenvalues and so on. And for higher lengths, I've checked this up to a number of particles because it becomes more and more complicated as you have more and more variables. But so so we have good checks for this at the moment numerically, and we have a good idea of how to prove this. So, well, it's 12 now. So basically, it goes via some dynamical model, and this is Vincent's world. So of course, there are Macdonald polynomials, Hecke algebras, and all of these kind of things. But we have a good idea of how this would have to be proven. So basically, you make the particles dynamical; they're allowed to move. They're governed by a Macdonald, basically by a Ruijsenaar-Schneider model with a Macdonald operator, and you can take some freezing limit in which the particles sit at their equilibrium positions, and it becomes this spin chain. And sort of this is how somehow all these Hecke algebras and Macdonald polynomials and so on show up for this spin chain, which is not clear at all from the way that I formulated it. But so I hope that we'll be able to get closer towards the proof of this conjecture by the end of this week. And this is what I wanted to tell you. So thanks. Everybody's a bit overwhelmed.
Just if you have an explicit tentative formula for the eigenvector, can you explain why it's not just, can't just plug it into the eigenvalue equation and verify that it's okay?
So yes, so the reason is basically are these multi-spin interactions. So even for the so for these Macdonalds, so these Macdonalds that I wrote down, they're not actually not obviously equal, but you can check that they are at least reproduced by this formula. But even for these, which are, so acting on this with the shift operator is at least easy. But even on acting on this with the Hamiltonian is already complicated, exactly because in these long-range interactions here, so this particle, it can start here, but it can actually sort of, if you have just one excited spin, it can move here, it can move all the way over here and actually interact, but it could also already sort of fall off here. And maybe another excited spin could be picked up over here and so on. So actually, when you do this explicitly, you always get big sums with complicated coefficients that you have to compute. So it might be possible, but it's certainly, there are easier ways of doing this, going through this dynamical model. So this is quite different than from Haldane-Shastry, where this is actually not so hard to compute, and you get the action of this color zero Hamiltonian in this case, basically.
Maybe another way, I think the Hamiltonian is very complicated, but you have some kind of momentum operators, which are much more easy to diagonalize. So we go through these momentum operators.
Yes, which, well, I guess in a way is what I did for the one particle sector there explicitly, yeah. Yes?
Any speculation about the physics? Is it gapless? Is this
Right, so these are all things that I don't really know, I don't really know anything about yet. It's too early, but these are of course obvious questions that I will definitely address in the future. Yes, so the Haldane-Shastry model is known to tend to this level 1 Wessel-Witten model. So of course, it's interesting whether this sort of, there's some sort of mass if you turn on this Q or what happens.
You don't even know if it's gapless or...
I don't know, at the moment I don't.
But we have the spectrum.
For finite length, we know everything, but for, of course, thermodynamically, this is a little bit of work, and I haven't looked at this yet. Yeah, no, of course. So I hope that when I'm here next time, I will be able to tell you more about that. Yes. Yes, so roots of unities and thermodynamics. Unfortunately, not really anything yet.
You said roots of unity, they are additional degeneracies.
Yes. So this is actually quite. So I've just looked at this sort of by building the spectrum, because this description works always, I think. So it's very easy. You don't even have to diagonalize Hamiltonian numerically. You can just build these things and get this. So of course, that I get these sort of kind of very regular patterns that I drew before and I erased is not so strange, because you have this strict additivity. So energies will add. So if you somehow, if your sort of basic, if your Macdonald energies are nice enough, then it's clear that by building this, you will get some, you will just build some sort of crystal kind of, some very regular structure, except that it's not infinite, because you have this, you can only add so many Macdonalds at the same time. So this is why you get this sort of, these finite sort of structures there. So you can compute the degeneracies, and they are really spectacular in that case. So, well, I don't really remember, but if, for instance, if you have 10 sites or 20 sites or something, then the Heisenberg model has maybe 150 dimensional eigenspaces maximally. Haldane-Shastry has maybe 10,000 dimensional eigenspaces, maybe, and this some roots of unity, we will have like maybe 50,000 dimensional eigenspaces. So they're really much higher, bigger than for Haldane-Shastry, interestingly. And yes, so I think this is definitely something that I would like to understand, because it's, well, lots has been developed already for these roots. I mean, the representation theory and so on is already known. So it would be cool to understand how, how the spectrum really how it's built up in that case.